Thanks, Nathan. And thanks, everybody. It's a pleasure to be here, both because we are neighbors and also there are a lot of familiar faces in the department here. It's really fun to be hanging out. So I'm going to tell you a bit, eventually, I'll tell you about some work that's going on in my group now, but I want to kind of start with the basic notions that we're interested in exploring in our experiments, which are kind of, you could, basically group as, what kind of phases of quantum matter can exist, what are the basic ideas that classify one phase from another, and how can we realize them and probe them in the lab. So I'll spend most of the time on introduction. I'll tell you a bit about the specific type of material systems that we like to work with and why those are a versatile platform, and then I'll tell you about some recent results where we can create band structures that are very susceptible effectively to instabilities towards either topological order or symmetry breaking, and combinations of the two, and why that might be interesting beyond just kind of the zoology of correlated states. So let me get this pointer out of the way here. Okay, so let me start with just sort of a very basic idea of, what do we mean by a phase of matter? So this is, it's unfortunate. Water's the material that we're most familiar with. It seems really commonplace, but of course it has a very complicated phase diagram, so it's actually a terrible kind of introduction to sort of what's a phase of matter. But it does have one feature that's useful. So when we think about a phase of matter, one way to think about its definition is some kind of, there's something that is distinguishable, that there's some equilibrium properties of one phase that are distinguishable from another phase. And also that should happen for some finite region of parameter space. So, just some different microscopic or, organization of water molecules and water vapor, water liquid doesn't constitute different phases, but, some kind of macroscopic property. And one of the consequences of that, right, is that there's a discontinuity when you have a transition from one phase to another. But there are actually two different kinds of one way to look at it is that there are two different kinds of phase transitions. So if we look at the vapor-liquid phase transition, for example, it's rather different from the liquid-solid phase transition. In particular, you can go from vapor to liquid, and that's a phase transition, and you'll certainly notice that. But you can, if you do it in the right way, there's a trajectory in parameter space here of temperature and pressure where you won't know the difference, right? If you go around this critical point, you can just go smoothly from a liquid to a gas, and you won't notice anything qualitative changing. So that's one kind of phase transition, right? There's sort of a removable phase transition. The discontinuity is physical, right? I mean, just ask this hawk. He was soaring in a bunch of water vapor, and now he is experiencing something different. But that's actually not what I want to talk about today. Rather, I want to talk about the other kind of phase transition, the type that's not removable, right? And the type where there's really some intrinsic difference between the two phases that you can't get rid of, right? And so the classic example of this is symmetry and symmetry breaking. So if we go back to this, let's say this picture of water liquid and water ice, there's a difference between these two phases, and that difference is that the ice crystal breaks spatial symmetries in a way that the water crystal does not. So for example, if you just think about calculating the expected value of the density in the liquid, it's going to be uniform. You can measure the density anywhere, but in the crystal, then that there's going to be some subset of things where it's the same. So if you translate a crystal by a lattice vector, you'll have this density that's the same as it was, where you started. But if you translate it by or rotate it by something that's not within the symmetries of the crystal, then you're not going to get back to the same thing. So in fact, you can distinguish the liquid and the crystal by different symmetries, and this is something that you can find out. If you can tell the difference between different water crystals by asking what the density is locally somewhere, right? And so that's sort of one way to classify different phases of matter. So symmetry breaking is behind a lot of the physics that we know and love, right? So there's this beautiful experiment that you do for elementary school students anytime you meet them, if you can, which is to levitate a piece of high TC superconductor on top of a magnet, right? And both the ferromagnet and the superconductor are basically consequences of broken symmetry, right? They're different symmetries that are breaking, but they're both distinguished from a normal metal or from a paramagnet by the breaking of some symmetry, spin symmetry or gauge symmetry. Going back to the time of Landau, it was understood that when you have this type of symmetry breaking, some kind of either let's say, whatever the expectation value of whatever operator it is that characterizes that symmetry breaking, back in the case of water vapor, and that's just the density of water molecules, but it could be any number of things, is either going to be discontinuous or some derivative of it will be discontinuous depending on the type of phase transition. But that's what you get, and that can happen either by thermal fluctuations or by quantum fluctuations, and these are all interesting fields of human endeavor within physics. So that was sort of all good until 1980 as a basic unified idea of what distinguishes one phase of matter from another phase of matter. But things got upset a little bit then by an experiment that was done originally in silicon, studying essentially the transport properties of 2D electrons in a magnetic field. So what Klaus von Klitzing and collaborators did was they were studying very flat systems of electrons with relatively small amounts of imperfections. And they were measuring the Hall effect and the longitudinal resistance in the same way that you would do in an undergrad lab to measure the density of electrons. What they found was surprising. In particular, they found that as a function of magnetic field or carrier density, it doesn't really matter which one, the Hall resistance, rather than being smooth, as you would expect for some metal, just tells you about the charge carrier density in the magnetic field, was characterized rather by these very flat plateaus in the Hall conductance that happened at the same time as vanishing of the longitudinal resistance. So it looked sort of like a superconductor from one point of view. You would measure the voltage that was developed across the sample as you passed a current in that same direction, and it would vanish. But at the same time, it had a quantized Hall conductance. And this quantization was nothing to joke about. So if you measured sigma xy, they found that in fact it was a multiple of just some elementary constants, e squared, the elementary charge, and Planck's constant, times some integer to an exceptionally high degree of precision, right? So 5 digits, I think, in the first measurement. And so, to some extent, the field that I'm going to tell you about was really born of this experiment, because it turns out that there should be something, right? In our idea of a phase, there should be something that would tell you the difference between being in this state that has Hall conductance e squared over h and the one that has Hall conductance 2e squared over h. But that turns out not to have anything to do with symmetry, right? And so that's sort of the original grain of a question that then gives birth to this other idea of topological order ultimately, and topological states of matter in general. So, but before I get to that, let's just think about a sort of phenomenological idea of how we can explain this basic finding, right? So one needs to explain the fact that you have a quantized Hall conductance, and yet your longitudinal resistance is also vanishing at the same point. And it turns out that's actually kind of easy to understand from a picture of what are called edge states. So if you imagine that there are one-dimensional modes that can propagate on the edges of the sample, but they propagate in opposite directions on the two edges of the sample, and nothing can move around in the bulk. The bulk is insulating. The bulk has a gap. Then it turns out that everything kind of works out. So when we think about resistance, right, resistance is intimately tied to scattering and dissipation, right? If you don't have any dissipation, then you can't have any resistance, because you would have Joule heating. So no dissipation means no resistance. And if you think about what's happening along this edge, you have some voltage between these contacts. This is your two-dimensional sample, and you have these probe contacts, and you have contacts that you use to inject a current. And along this edge, there's simply one quantum mode. There's an electron can go only in one state that actually propagates, and it only propagates in one direction. So there's no scattering states for an electron on this edge, except for the ones that scatter forward, the same state, right? It can only scatter forward, no matter what you put in the way. You can put disorder in the same place, right? And it can only scatter forward. And that means there's nowhere for a voltage to develop, because there's nowhere for this to scatter. These two things are tied. By the same token, if there's nowhere for it to scatter, then an electron in this edge state will have the potential that it started with in this contact. And the same thing is true for the electron. Any electron traveling in this edge state will have the same potential. So if you then calculate the Hall voltage, you'll find that it's simply given by n e squared over h, right? In the same way, because e squared over h is simply the conductance of a single quantum mode. So this was an idea sort of due to Halperin, but there were a number of other arguments that were advanced around the same time. In particular, what this tells you is that the number of chiral edge states is the thing that's related to this quantized Hall conductance. So 3 e squared over h means you have 3 edge states moving in opposite directions on the two sides of the sample. And this turns out you can sort of understand, because an electron in a large magnetic field, we know what the spectrum, that's a sort of problem that you solve in your first year quantum mechanics class. It's given by Landau levels. So classically, I think I had this on a previous slide, apologies. Classically, an electron undergoes cyclotron motion, and you can think about Landau levels as simply the sort of Bohr-Sommerfeld quantization of those cyclotron orbits. And you can have an orbit in one place in the sample, or you can have an orbit in another place in the sample. They all have the same energy. And there are many places in the sample where these orbits can happen. And so you have a level that has many electronic states, but they all have the same energy. And again, arguments from this sort of time period were essentially able to show that for each Landau level, if you have a sample edge, then in fact, there will be one state for each Landau level that's going to be large, that's going to bridge one contact to the other. And that's your edge state, and you can show that it's sort of localized near the edge of the sample. So in a sense, this number of edge states is just counting the number of levels. This was sort of felt to be somewhat understood. But around the same time, actually, an argument from, if you want, a completely different point of view also popped up, which was due to David Thales, for which he justly won the Nobel Prize a couple of years ago. And this was an argument that had nothing to do with the idea of edges at all, but rather it had to do with trying to just calculate what this Hall conductivity would be from a different argument that had to do with what the bulk wave functions actually were. And what Thales and K, N, and N, who are the other authors on this paper universally referred to as TK and N, found was that you could in fact find the same formula. You could find that it's quantized in units of e squared over h, but that this quantization actually arose from a topological invariant. So what that means, if you look here, there's some line integral around a closed surface in 2 dimensions, and essentially single valuedness of the wave function tells you that this has to be some sort of integer. You're integrating some phase, and that phase has to be some multiple of 2 pi. That's ultimately where this quantization comes from. And in order to find, and this will be different. These u's are the different band wave functions, so depending on what kind of material you have, those u's may be different, but you'll find an integer no matter what if you have a filled band. And then to calculate what the actual Hall conductance is, you simply sum over all of these filled bands, and you're guaranteed to get some quantized Hall resistance, as long as you have a filled band, meaning as long as you're in an energy gap. Now, for most materials, that's not a very deep statement. If you measure the Hall conductance of your typical insulator, you will find that it is indeed quantized and indeed vanishes, right? And that's not a very interesting statement, but this argument says only that it can be any integer, and indeed, when they calculated it for Landau levels, they found that that integer would be 1 per filled Landau level. But this makes no particular reference to the details of the edge, right, or to anything about the system being confined. It simply says that sigma xy is something related to the bulk properties of these bands, in particular something about their topology in momentum space, but their topology. So in fact, this is not exactly the same statement as before, because before we were told that each Landau level contributes 1 edge state, and so if you sum over Landau levels, you'll get the number of edge states. But what this formula is actually telling us is considerably more general. It says you should really sum over this topological invariant. It's also called a Chern number, and I'll probably refer to it that way interchangeably. You should really sum over the Chern numbers of all the occupied bands, and that'll tell you the number of edge states. But they need not be 1. They could all be 1, 0, -1, 10, whatever. They'll all be integers, but you can just sum them up, and that'll tell you the Hall conductivity. So in fact, if we look more carefully at this paper, what TK, N, and N were solving was not just the Hamiltonian for electrons in a magnetic field. They were, in fact, solving a model that's a little bit more complicated, but still is made up of 2 scenarios that most people are familiar with. So I've already told you, a magnetic field, 2-dimensional electrons, the energy spectrum is described by Landau levels. That's something that most people have seen. In a periodic potential, in contrast, it's essentially described by plane waves. They're block waves. They're slightly different from plane waves, but we know from, back from the 1920s that in a perfect periodic potential, electrons can just propagate, and they'll have their wave function slightly modified by the existence of the periodic potential, but basically they're plane wave type states. It turns out that if you have both of these at the same time, which is the problem that TK and N were calculating, it's somewhat more intricate, and it actually has a rather strange pathology. So in particular, you can solve the model of a two-dimensional electron in a magnetic field simultaneous with a periodic potential exactly, pretty easily, as long as this number, which is the ratio of magnetic flux quanta per unit cell of this lattice, is a rational number. The strange thing is that if you solve this, you'll find that it has exactly q distinct eigenvalues. And that's pretty strange if you think about a quantum mechanics problem, because this is just related to the magnetic field or the lattice constant, right? If you're a theorist, you can say, oh, I can change the lattice constant continuously. Realistically, if you're an experimentalist, it's a lot easier to change the magnetic field, but you can certainly change the magnetic field continuously. And yet, the function q, when p over q is a rational number, is a very discontinuous function, right? It's a very strange function to have. So it was Hofstadter, Douglas, later of fame as an author, and researcher on things non-physics, who first took this and solved this problem on a computer. And this is the solution that he got as a function of, this is the energy spectrum for this problem of an electron in a magnetic field and a periodic potential. This is the energy as a function of magnetic field, or alternatively lattice constant, really of flux per unit cell. And this is a very beautiful structure. It's one of the first fractals to actually pop up in physics. In fact, it popped up a year before the name fractal was coined, not by Hofstadter, but by Mandelbrot. But Hofstadter, like everything else, had some strange name for it. So if you've read Gödel, Escher, Bach, you know that there are a lot of strange names around in his lexicon. But this, is indeed has a lot of self-similar structure. If you zoom in, you'll find richer and richer structure on smaller and smaller energy scales. But there's obviously some large-scale structure, in particular what is continuous. So the bands themselves are not continuous. But what is continuous are the gaps, right? So if we look at all of these black regions, that's where there are no eigenvalues. And there are clearly large regions with no eigenvalues. So let's understand what TK and N did. They basically said, within this model, we can take all of the filled bands. Imagine that we fill up all the bands up and our Fermi level, the number of electrons occupies all these bands, but all these others above it are unoccupied at this particular spot. Then if I want to know the Hall conductance, I just need to sum up this quantity for all of the occupied bands. So if you do that, this colored Hofstadter butterfly is basically telling you what's the phase diagram for non-interacting electrons if they're put under these conditions of a simultaneous magnetic field and periodic potential. So in particular, right, red here means, let's say, a Hall conductance of 1. Blue means a Hall conductance of -1. Orange might mean 2, -2, and so on. And you can see that while, down here everything is rather monotonous, right? You just add one of these levels. If I go back, if I fill one of these levels, my Hall conductance just increments. That's the situation of Landau levels. That's the situation of the integer quantum Hall. In fact, much more general behavior is available once you get into these kind of regions of the parameter space where there are many of these bands very close to each other. And they have different Chern numbers for each band. As you fill them, then the Hall conductance is going to oscillate wildly. Anyway, this is sort of all theoretical ideas, not necessarily all that relevant, because for a real crystal to get to the relevant regimes where this sort of rich behavior starts to happen, you need extremely large magnetic fields. You need one magnetic flux per unit cell. Unit cells are a few angstroms in size, and so you need 10,000, 20,000 Tesla. But it is indeed a generalization of Landau levels, and it's a generalization that we'll return to at the end, because to spoil the punchline, this is now something that we can explore relatively easily in artificial lattices while maintaining the high quality. And that's, if you want, going to be the punchline of this talk. But first I have to digress for another several minutes. So, okay, so what's important about this idea of a topological quantum number? Well, it actually can be a useful thing, right? So one of the key points, right, is that we have this guarantee that for a given band structure, the Hall conductance will be quantized in units of E² over h. Okay, and that's a very strong statement because it means, for example, if you change a little bit the wave functions, let's say you sprinkle a little bit of disorder in the middle of your sample, the best that you can do is change it by a whole integer, but you can't change it by a tenth of an integer, right? And that actually turns out to be useful. So on the left here, this is I don't know how good the contrast is, but this is basically if you buy a precision chip resistor, right? You want a resistor, it has a certain resistance, right? And you want to order it, and you say, okay, I'm going to buy the most expensive one. Maybe it'll have 0.1% accuracy, maybe 0.01% accuracy, something like that. This is what you're going to get if you open up the package. You're going to see that it's a metal film, and there's these sort of thinner parts, that's the orange. And you'll see that somebody went in with a laser and cut it. Okay? And the way they did this is that they were measuring the resistance, and they went in with a laser, and they cut it until the resistance matched what they wanted it to match. Okay? And with that, you can get something on the order of a part in 10,000 accuracy. Topological protection, in a sense, at least in the context of the Hall effect, is much better than this, right? In other words, you can take some semiconductor wafer that has a two-dimensional electron gas, you turn on a magnetic field, and you don't have to cut it. You can measure it, and you'll find that, in fact, the resistance that you get is going to be E squared over H in appropriate units, right? To a part in a billion, right? Sort of regardless of what you do. Actually, most lately, and I'm sort of fond of this, you know, this the metrology standard that sets the value of the ohm recently shifted from gallium arsenide, a two-dimensional electron gas where one sees the quantum Hall effect of graphene, where it's, you know, for various reasons slightly more convenient. Admittedly, this type of setup is considerably more expensive than that one, but there's no way you ever do this well with this type of approach, right? So you can engineer the hell out of materials, but there's this hope that topological protection, just, you know, smartly applied, could actually get you something sort of for free from nature, right? So what? I mean, a resistance standard is in fact important. Standards are important. But there's kind of a dream, right? And that's a dream that I'll come back to at the very end, which is to apply this idea more broadly, in particular to apply it to quantum information. So there's an analogy, which I'm not going to dwell on too much, but maybe I'll spend a few minutes, between, let's say, you know, the type of topological protection relevant for quantum Hall and trying to apply that to the idea of manipulating and storing quantum information. So in particular, let me just sort of list the analogies, right? So quantum Hall, you know, what we care about is resistance. So what we care about is dissipation and scattering. And the analog in quantum information is decoherence. You know, if you have a quantum state, you want it to stay the same or evolve in some well-understood way without turning into something that you don't control, right? So the analogy of decoherence and scattering, you know, if you could eliminate decoherence in the same way that you eliminate scattering, then you get a quantized resistance in the quantum Hall, but you would essentially have an infinitely coherent qubit in this sort of other setting. And what limits this coherence in the case of quantum Hall, what it's really being limited by is the size of the sample and the size of the energy gap. So if you have a big sample, you know, maybe a millimeter or centimeter, that's very big. There's some exponential protection in two parameters. One is the size of the sample, and the other is the size of this energy gap and your temperature. So the same thing would be true here. You know, this coherence would be limited by, let's say, the size of this gap if you do everything right. And then the way this is supposed to work is that I haven't told you yet how to even do this, but basically, you know, the analogy in quantum information to quantum Hall is to be able to create states of matter that have essentially particles that in some space, it may be real space, it may not be, you can twist around each other. And the quantum information is essentially stored in the nature of the knots that you tie in them, right, as a function of time, let's say. You adiabatically move them around each other, and then there's clearly a sort of quantized difference between, you know, how many times one line goes over the other, right? You can put this on sort of more formal setting by talking about invariance of certain knots, right? But that basically gives you something that's going to be an integer, right? And it can't be something that's not an integer unless you cut the whole thing, which is sort of like saying the quantum Hall has to be an integer unless you sort of do something very violent. So in order to do this, though, you sort of need to rethink what you mean by particles. So we know, I mean, maybe condensed matter people will be very familiar with this idea, but maybe for the non-condensed matter people, you know, we know that, you know, again from our quantum mechanics classes, that if you have identical particles, you can more or less show that the fact that probability should be conserved and amplitude should be conserved basically on sort of identical transformations means that you really can only get two things. Either when you interchange particles, you get the same wave function back, or when you interchange particles, you get the same wave function back with an opposite sign. Those are the two options that you have. And one of those exchange statistics corresponds to bosonic statistics, and one corresponds to fermionic statistics. And all the particles we know about in nature that we regard as fundamental are one of these two things. So that's true. It's true, but it's only really true in 3 dimensions, right? And of course, we live in 3 dimensions, so it's true for us, right? But it's not necessarily true for a 2-dimensional universe. And a 2-dimensional universe is not necessarily fanciful, right? You know, and if you restrict particles to 2 dimensions, then nothing prevents them from behaving like this. Of course, you can't make new elementary particles, but in condensed matter, it's very normal for us to think about what the elementary excitations of a system are, and what, you know, sort of what are the minimum energy quanta that one can inject into a system. And if you have a 2-dimensional system, nothing prevents you from obeying only the laws of 2-dimensional physics and not 3-dimensional physics. And in particular, in 2 dimensions, you can get something more than bosons and fermions, because the notion of handedness has a meaning, right? If you really only have a 2-dimensional system, then rotating particles around each other clockwise or counterclockwise are distinguishable operations. You can't take the system and flip it. You can't take the particles out of the plane to undo that operation. And as a result, you're allowed to have many particle wave functions that transform with some arbitrary phase, with any phase, and hence the name anyons, right, as distinguished from bosons and fermions. And that turns out to be sort of the key ingredient for sort of trying to extend these types of ideas of topological protection from quantum Hall systems to quantum information. Actually, there's a little bit more detail that goes into this that I'll just mention and I won't come back to, which is that even among anyons, they're really only a very special type of anyon that can do this sort of quantum information trick for you. You need essentially their exchange statistics to not be just described by some phase, but rather by some matrix. You need a set of these different types of anyons that will transform into each other when you wrap them around each other. You can ask Kirill if you have any questions about this. He's sort of a world expert on this, having written both of the essential technical papers, but also some of the nicer popular expositions. I should have taken a picture from his rather than from this other one, but hopefully he'll forgive me. But you know, the sort of, you know, all of this sounds very nice, right? But there's the question of, well, that's great that it can exist, but you know, I know about bosons and I know about fermions and I know about electrons and I know about ions, and those are mostly fermions. So can I get this to actually work, right? And so that's sort of where we turn to next. So it turns out that the answer is certainly yes, that such things can exist, right? And they're really encoded in an experiment that was done, you know, essentially the same experiment that I showed you at the beginning of the quantum Hall effect, done in even cleaner material. So the main difference between the previous one is that the material has fewer defects, the temperature is lower, the magnetic field is higher. I'll explain why all those things are important in a few minutes. And what these experimenters saw were plateaus, very much like what I showed you before. So regions of electron density and magnetic field where the Hall conductance became quantized. But rather than becoming quantized to an integer multiple of e squared over h, it became quantized to a fraction, a rational fraction of e squared over h. Actually, there was just a paper this year where this quantization of a fractional quantum Hall state was measured, and it's almost as good as the one for the integer state, maybe an order of magnitude or two worse. But you know, this is again fractionally quantized to some part in, you know, a few parts in a billion, a few tens of parts in a billion. So what exactly is going on here? It turns out, I didn't mention this earlier when I should have, but this Hofstadter butterfly, right, and the idea that you have all of these different states that can have integer quantum Hall states, you can actually prove that that's all you can get in 2 dimensions if your electrons don't have interactions between them, right? So if you just consider the physics of independent electrons, that actually limits you. This is not a possible result within that context. So it tells you already that something richer is going on. Again, in condensed matter physics, most of the rich physics, not all, but most of the rich physics arises when you have interactions between electrons, because that, if you want, that's where our ability to calculate things very well breaks down. So we don't typically know the answer beforehand. That certainly was the case for this experiment, which was highly unexpected and really changed the way people thought about physics. So what's going on? So it turns out that if we think about what's happening here, you can, these fractionally quantized Hall plateaus are happening at partial occupation of a Landau level. So let me remind you, right, these Landau levels, there are many states. They all have the same energy. Okay, but now we're going to fill a third of them. So how do I choose which ones to fill? Right? So this is it's an exercise in degenerate perturbation theory, or degenerate, it's not really perturbation theory as it turns out, but you have these very degenerate Landau levels, you're filling a third of them. You can't choose based on kinetic energy. Usually if you have an energy band that disperses, then we fill the lowest energy states. That's sort of a good guess to start with, right? But here there are no lowest energy states. All the states have the same energy. So the only thing that lifts that degeneracy is the interactions between electrons. And this is a very simple Hamiltonian, right? It's just mutual repulsion between all of the electrons in the system. Very difficult to solve on a computer, very difficult to solve analytically. You can solve it on a computer for like 10 electrons or 15 electrons, something like that, but you certainly can't solve it for the numbers of electrons that exist in a real system. It, of course, depends on how many electrons you have. And Laughlin famously basically guessed the answer, right? So he guessed a variational wave function, something that, this looks like a reasonable guess. These z's are the coordinates of the electrons, and this m factor sort of, as long as it's not zero, it encodes the fact that the different electrons avoid each other pretty well, and so that sort of makes sense. You'd want something that would minimize the Coulomb repulsion between different electrons. And the amazing thing about this wave function is that if you calculate what, first of all, it has an energy gap, so it itself has an energy gap. It's an insulator. But if you calculate what the lowest lying excitations are, how do I inject energy into the system? The easiest way you can inject energy into the system is in packets of electrons that have a third of an electron charge on net and have, in fact, anionic statistics. They have the same exchange statistics that you would like. They're just not the non-abelian kind, but they have the regular kind of exchange statistics. It turns out there are also much more exotic possibilities at specific other filling factors. This was the first one for all of the odd denominator filling factors. So the key point, though, for us technically, certainly, and for this field technically, has been that this is a pretty good solution to this Hamiltonian, to the ground state of this Hamiltonian. But if I start to, for example, add disorder, then that's going to lift this degeneracy in a different way, right? If the potential is higher here than it is here, then I'll put an electron here before I put one here. Disorder tells me where to put my electrons rather than allowing me to make these sort of exotic types of states. But once your system is clean and you have interactions, these are the type of states that can appear. And in fact, they appear very generically in many models in condensed matter. And this is sort of a whole industry. The key thing, though, is that, in fact, this is really something different than symmetry breaking. This is something where, actually, by definition, there's no way to locally tell that you're in a fractional quantum Hall state from the ground state itself, right? But you can tell from the statistics of the elementary excitations with this. And that's very different from symmetry breaking, where you can always tell locally what's going on. But it's precisely that non-local element, in the case at least of the non-abelian states, that allows you to encode quantum information in a way that even a local perturbation isn't going to be able to screw up. Right, so just before I move on, right, let me just comment, and I'll come back to this again, that we have a lot of examples experimentally in the lab of symmetry breaking. Symmetry breaking is all around us all the time, right? We have very few examples of topological order. In fact, there's really one Hamiltonian that we know how to realize that is for sure has topological order, right? And that's the Hamiltonian of a partially filled Landau level. There are a couple of others in so-called spin liquids that might have it, but it's not so clear, and it's not so clear that they're actually gapped, and that there's still a lot of effort. So maybe there's two, right? There's, I don't know, a million different ways to get symmetry breaking, like every crystal you can imagine, everything more or less interesting that condensed matter physicists study is probably characterized by symmetry breaking. So we hope that we can find something more. Okay, so the way that we do this, whether we do it intentionally or not, is a better question. But what we actually study are van der Waals materials, and graphene is sort of the king of van der Waals materials. And we make it in a very low-tech way. We still use Scotch tape, and you peel pieces of graphite, and you can make monolayers of graphene, which are, if nothing else, two-dimensional, right? So 2D is important if we want to ultimately make anyons. If we want to explore a lot of this physics, 2D is kind of essential. And the reason that you can do that so well is that graphite is covalently bonded in the plane, but of course van der Waals bonded between planes. So it's very easy to make those types of structures. This is what it looks like on a substrate. Sorry, there should be a scale bar, but this is maybe 50 micron field of view. So you get sort of tens of microns flakes. They're 1 atom thick. They're relatively free of defects intrinsically. And so people did that. The first experiments were from Manchester and my PhD advisor at Columbia in 2005. But sort of a long way to go for this type of physics. So remember, disorder is key, right? Exploring all of this type of exotic physics in 2 dimensions really requires you to make electron-electron interactions dominant. If you just are relying on a disordered system, then disorder will choose your ground state for you. It won't let interactions choose them for you, right? And so if we compare, so these are data from the early 90s in sort of the state-of-the-art gallium arsenide quantum wells. These are grown by molecular beam epitaxy. People know very well how to do that type of growth so that you get a very defect-free 2-dimensional electron system. And you can see there are many peaks and there are many dips, and each of these dips is a fractional quantum Hall state. So you can think about that as a vacuum from which the excitations are these anyons. Some of them are indeed thought to be non-abelian. And this is where things were 1993. This is where graphene started, and it looks like there's a lot of dips, but actually there's not so many dips because this whole plot would fit almost in the width of this laser pointer to the degree that I can hold it still. So it's all within less than a Landau level. So there's a lot of physics missing, and the reason for that is that originally graphene was fabricated on dirty substrates. And graphene itself is nearly free of defects. A graphite, just, the energy cost for deleting a carbon atom is very high. On the other hand, anything you put nearby will sort of mess it up. So if you put it on a piece of glass, glass is not a perfect material. Glass is basically amorphous, and there's lots of trapped charges and dangling bonds. And that will basically tell the electrons where to go. It'll say, go where there's not something to repel you. So people knew that. They figured it out pretty quickly, and they did really heroic experiments to take these single layers of carbon and suspend them, so to remove the substrate completely. So you just have this 1 atom thick membrane. And that turns out to help a lot. So for example, what they were able to do was observe for the first time fractional quantum Hall states in graphene, right? So that already tells you that electron-electron interactions are indeed choosing your ground state rather than just disorder. The problem is with this approach is that it's very difficult to do experiments on a 1 atom thick sheet that's suspended, unless what you want to do is make it vibrate, right? Which is fine. But anything having to do with, say, manipulating individual quasi-particles, individual E/3 or E/4 charges, which is what you'd like to do, is exceedingly difficult in this type of geometry. So, some years ago, we sort of stumbled on the idea of trying to do this in a substrate-supported geometry, but trying to eliminate what the basic problems were, which we thought were some combination of the fact that the typical substrates were sort of corrugated, and the typical substrates had lots of trapped charges in them, right? And if you're talking about electrons in your 2D material, then what you'd like is for there to be no local charges nearby, because if there's a local charge, it's going to push the electron away, and if it's a positive charge, it'll suck it there. And again, it's going to choose your ground state for you. We don't want that. So the answer to that turned out to be this other material, hexagonal boron nitride. It looks very similar. The only difference is that the atoms here are both blue, whereas the atoms here are red and black, meaning that one is a boron atom and one is a nitrogen atom. So they're different. And actually, that difference is the difference between having a gapless 2-dimensional electron system, so something that has lots of electrons at the Fermi levels, effectively a metal or a semi-metal, and an insulator. So hexagonal boron nitride is like a large gap insulator. It's got a 4 or 5 electron volt band gap. But chemically, it's kind of similar in the sense that all the bonding is in plane. Here it's ionic, but out of plane, they're both van der Waals. And right around the time that we were looking for a substrate, a group in Japan at NIMS had figured out how to grow large single crystals of this stuff at high purity, which through a long story I'm happy to tell offline, some of them were lying in a drawer near where we were trying to do this. So this is what boron nitride looks like. You know, it's an insulator. It's much more transparent, a little harder to see, but basically that's what it looks like, kind of blue. We spent some time figuring out how to, Corey, Dean, and I, back when we were both at Columbia, spent some time figuring out how to pick up these individual layers and stack them on top of each other to make heterostructures. So this is what a heterostructure looks like. Let me, you know, you take graphene, you put it on top of boron nitride, and that's basically what you have, and then you can sort of make electrical contacts and figure it out. So that turned out to help a lot also. So again, we made a little bit of progress. We really didn't improve much on the quality of these suspended membranes, but we did improve on the sort of experimental tractability of dealing with it, because now you had something that wasn't going to collapse or break or blow up, you know, just because you looked at it. These are somewhat more robust. We could do some more different types of experiments. Again, we can see kind of fractional quantum Hall states. But just again to compare, we saw fractional quantum Hall states at, you know, let's say a third, right? That's sort of the biggest fractal. That's the easiest to realize fractional quantum Hall state you can have. Whereas again, in gallium arsenide, for many years, they were studying, you know, the 15ths. You know, these, the bigger the denominator, the weaker these types of states are expected to be, and indeed, the weaker they are, and we're sort of nowhere near that. So, so it's only in the last year or so that we finally sort of cracked this problem. This is some data from my current group in monolayer graphene, and the key point turned out to be not that there was something wrong with the graphene, or not even there was something wrong with the boron nitride, but there's something wrong with everything that's not graphene or boron nitride. And so, you know, something that took us a long time to figure out and still kind of boggles my mind is that what limited the, you know, what our main disorder was in prior to this year was the fact that even though we had, you know, this perfect graphene layer and these perfect single crystals of boron nitride, to control the charge density, we were using gates, and those gates were made of metal. And if, you know, if you're a semiconductor physicist or a condensed matter physicist and you want to put some metal somewhere, you take your sample and you put it in an evaporator, and you boil some metal, and the metal gets on the sample, and, you know, that's your gate. Then you apply potential to that, and if there's a dielectric in between, that's how you make a transistor. Well, it turns out that metal, you know, I was taught, wrongly as it turns out, that metal is an equipotential. Turns out that's not exactly true, right? It turns out that different facets, little grains of metal, have slightly different work functions on the different facets, right? And so if you're evaporating some metal, then these different work functions on the different facets basically look, from the point of view of the graphene, they look like, oh, this is a little different potential here and then different potential there and so on. And that was the main source of disorder in our sample. So our graphene, you know, you want the electrons to just decide mutually what kind of ground state to be in, right? But actually what they were doing was they would see a metal grain that had a slightly different work function, and they would go stand under that, and the other one would go to the one that had the higher work function, stand under that, and that was sort of the main issue. But we figured out how to deal with that, because in the same way that we have graphene, we can of course just not make it any thinner and just make it graphite, and graphite is a single crystal, and it doesn't have any dangling bonds, and the work function is all the same, and that turned out to be kind of the key improvement that let us do now the same type of physics in graphene that people had done in gallium arsenide for a long time. So here's some data from our lab recently where you can realize, you know, dozens and dozens of these fractional quantum Hall states, including very exotic types of fractional quantum Hall states thought to be non-abelian. You can realize quantum phase transitions between them where you change their symmetry, and so on. And doing all of this type of mapping as a function of density, as a function of different types of conjugate fields to various types of order parameters you might want to realize, is sort of something that now is something we can do in one sample. Back in the days of semiconductor physics, this is often something that would take tens of samples over many years. The physics is often the same. There's sort of a few tweaks so far, at least in this type of data, but you can sort of get it all very quickly. We do this mostly by capacitance measurements, although you can do it by transport measurements. I'll say a little bit about capacitance measurements, so that's what I'll show you afterwards. But this is essentially measuring the capacitance between one of these gates and the graphene itself. So if you measure capacitance, you're effectively measuring the energy required to move charge around the system. If your system has an energy gap, if your 2D layer has an energy gap, it costs you a little bit of extra energy to get an electron in, because you have to actually raise the Fermi level. And when you do that, you'll see the capacitance go down or up in the particular color scale and geometry that we were using. So these sort of dark lines are, in fact, energy gaps. Each of these is an energy gap. And every time you see a little pinched sausage, that's a gap closing as you have some quantum phase transition between them. OK, but I'm not going to tell you sort of about fractional quantum Hall physics. I want to tell you about something a little bit more new, which is to try and revisit this Hofstadter butterfly. How much time do I have, by the way? Perfect. OK. Yeah, perfect. So I'd like to revisit this problem, right? Because in the same way that a partially filled Landau level was this ideal venue for understanding topological order, and indeed Landau levels are sort of the prototypical venue for understanding just this idea of a topological invariant, then this Hofstadter butterfly is basically the generalization of that, right? And so there may be some generalizations of these ideas that might be useful, and it turns out this is something that's exceptionally difficult to study for the reasons that I told you, right? Crystal lattices are very small. Actually, you can make artificial lattices, right? I can go to the clean room and punch a bunch of holes in a dielectric. It's hard to do that really well. It might be possible to do it well, but it's hard to do it perfectly. But it turns out we can sort of revisit this rather naturally. And the reason for that is that this way in which we're assembling these structures is very manual, right? And it relies on assembling fully formed crystals together, right? So these crystals already exist. And I can put them on top of each other. But I can put them on top of each other in any orientation that I want. So in particular, I could take a sheet of graphene and a sheet of boron nitride and then choose at what angle I put one on top of the other. And if you can look at this without getting nauseous, you can see that depending on the angle, you will get either not much structure that you notice, or you'll get a lot of long wavelength structure. And this is basically a moire pattern, right? It's the same, it's just interference between two lattices, if you want, of different wavelengths. It's the same thing that you use to make moire fabric, which seems to have been fashionable in the 18th and 19th century. It's still de rigueur for clerical headgear. But this is something that actually you can make in these types of samples. So these are STM micrographs of graphene on boron nitride. This is not the graphene lattice. These are much larger wavelength corrugations that just derive from this interference. And because the elastic energies for deforming these states in the plane are rather high, this is going to be a very regular lattice. It's all going to happen sort of in the same way everywhere because it's just given by the interaction between the two. Actually, most of the artifacts in these things, these sort of irregularities, we think are actually due to the fact that when you do STM, the STM is about as invasive as can be, and it's actually pushing the atoms around. But these lattices are actually very regular. And they sort of hit the nail on the head as far as wavelength, because basically instead of having it be 3 angstroms, and therefore you need 10,000 Tesla, it's 10 nanometers, which means you need 20 Tesla. And 20 Tesla is something that we can do in the lab pretty easily. So let me just sort of pause for a second and tell you what we actually measure, because we don't measure this Hofstadter butterfly directly. We don't tunnel into it, or we don't do spectroscopy. Rather, we just measure the presence of gaps, right, the presence of energy gaps. And it turns out that within this picture, if you map it to the variables we turn, it's very simple. That the number of electrons and the number of flux quanta per unit cell are just related by a linear equation, where this t and this s are integers. And actually, this t, the slope of these lines, tells you exactly the Hall conductance, right? And that's provable on very general grounds. Whereas s is effectively telling you about the block band index. So this Hofstadter butterfly is basically telling you should have gaps that have integer t and some integer s, but s not equal to 0. That's sort of the signature of the Hofstadter butterfly. So this is what this is in this particular case, it's resistance data, but what resistance data looks like with no superlattice. And what you see is that there are lots of lines. Each of these dark patches here is a gap. And they all trace back to 0. V gate is controlling the electron density. B is controlling the flux. And they all trace back to s equals 0. They all have quantized t, as they should. They're all integer quantum Hall states. So this is not the Hofstadter butterfly. This is what Landau levels look like. When you turn on the superlattice, right, which means for us looking at a different device that has a superlattice of a certain size, you see that many of the features associated with gaps, here they're all different colors. Don't ask me why. It was a tough day in Tallahassee when we took this data. Some of the gaps trace to 0, right? Like this dark black one, right? That's just charge neutrality. It's an insulator, it traces to 0. But some of them don't trace to 0. So here you have one that doesn't trace to 0. In fact, you have many that seem to originate from some finite charge density. And that's exactly the sort of signature of the Hofstadter butterfly. There are a number of integers at different integers. Here you can see actually all of them mapped out, 0, 1, 2, 3, 4 in appropriate units. All of these are integer quantized quantum Hall states, but they're quantum Hall states that are not due to Landau levels. They're due to these gaps within the Hofstadter butterfly spectrum. So this data was taken a few years ago, right? Several other groups sort of did the same thing at the same time. What I'll do in the last 5 minutes of the talk is just revisit what happens in these very clean devices that we now know how to make. These were not done with a sort of graphite and boron nitride all single crystal encapsulation. So this is what sort of some subset of the data looks like. I'll show you sort of a fuller data set at the end. There's a lot of lines here, right? It's very difficult to look at this and understand what's going on. There's certainly some big lines, there's some small lines, there's lots of lines that cross each other. Okay, it's a little bit hard. But we can classify these lines by what I just told you. So in particular, we have a couple of, we can classify them all by their trajectories in this space, right? And we have two types that we're very familiar with. We have integer t and 0s. Those are integer quantum Hall states, right? No superlattice physics. The s is all from the superlattice physics. And nothing special, just integer quantum Hall, right? That's von Klitzing, 1980. Then we have some states that have fractionally quantized t, right? That basically means there's fractional charge in the system. There are these anyons of some kind, right? Again, that's okay, Stormer, 1982. Then we've got some of these gaps that have integer t and integer s. That's the Hofstadter butterfly. That's all of the different gaps in the Hofstadter butterfly. Pretty clear. But there's a bunch of gaps that don't fit into this pattern, and that's kind of the new thing in these very clean samples. In particular, there are gaps that have integer t, right? So integer quantized Hall conductance, and fractional s. That's sort of strange. And then there's ones that actually have both of these fractional. When I say fractional, I mean a rational fraction. I don't mean 0.752364. I mean like a third, right? Or a half. And so there are a number of these that whose slopes are precisely quantized. So you can understand this, if we look a little bit more in detail at the precise definition of these quantum numbers. So S is really telling you about how many electrons are stuck to each unit cell, right? So if you change the number of unit cells in your system, how many electrons would move in or out? So it turns out if you have a fractional S, right, that's basically telling you have some fraction of an electron glued to each unit cell. There's two ways you can imagine doing that, right? One is if your charges are fractional, right? But the other is just if you're wrong about the unit cell, right? If your unit cell is twice as big as you thought, then you only have half as many electrons per unit cell as you thought. In other words, what's the fundamental periodicity of the system? Did it break a symmetry? Did it break the symmetry of the lattice? T is much more subtle, because T, it turns out you can prove, again, on sort of pretty general grounds, that a fractional T is not something you can get from symmetry breaking. You have to get that from fractional charge. T is the Hall conductance, right? And there's a very general argument due to Laughlin that if you have a fractionally quantized Hall conductance, there has to be some quasi-particle in your system that has a fractional charge and therefore fractional statistics. And this, is sort of the signature of topological order. So these fractional T fractional S states, they sort of have to have a fractional charge. These integer T fractional S states, they could, but it's unlikely. They're probably just symmetry broken. Right, so the way it turns out to think about this is that, these are, in both cases, the key point, right, is that neither of these things happen in the Hofstadter butterfly. This is many-body physics. It's the interaction physics that's happening. So if you want to start to get a physical idea and be able to try to do some calculations, our approach was to think about, all right, let's forget about those for a second and just try to understand what's going on at the single particle level. What's our band structure? Can we extract our band structure? And it turns out that you can, because we know what the Moiré potential looks like, and we can model it, and we can model we can measure the Chern number of the underlying bands, because these states are still relatively weak compared to the non-interacting ones. So for example, we measure the slope of two adjacent integer lines, and we know how much the Hall conductance changed, because it went from one to the other. So we know the Chern number of the underlying band, and that's something that we can get out of a simple model for the periodic potential in the magnetic field. And this is what our band structure looks like in this particular regime. You know, there may be a little bit of quantitative differences, but this reproduces the correct topological invariance of the underlying bands. And then what that means for these interacting states is that what they represent are many-body instabilities of this band. Now, there's one really big difference between this and a Landau level, which is that this has a lot of dispersion, right? You know, it's not disorder that chooses where the electrons are going to go, but it is the lattice would say, well, yeah, fill the lowest bands first, right? Why would you sit around filling some high-energy state to create this entangled state? But it turns out if you sort of do some estimates that, you know, the strength of interactions is kind of comparable to that, right? They're competitive. And in fact, sometimes, you know, in the narrower parts of these bands, here's a Chern 2 band. That's rather different from a Landau level, but it's not very broad here. Whereas here, this Chern 1 band is very, very large. And in fact, if you look through, it sort of matches up where you have very large bandwidth. You don't get much in the way of correlated states, but where you have thin bandwidth, you do, and you get different things. So I'll just conclude by sort of walking you through the zoology and then take questions. But essentially, when we have higher Chern number bands, let's say Chern 3, what we typically see are symmetry broken states. And we can confirm this because now we know this very well. We can do calculations with our collaborator, Mike Zalatel, who can run calculations. Once we give enough information about the Hamiltonian, we can do a many-body calculation. And we find that, in fact, the ground state, you know, taking everything that we know about this system, indeed, under these conditions, breaks a symmetry. So each of these dots is a unit cell center, right? But you see some unit cells are different from others. In fact, the unit cell here has increased in size. Same thing is true at under some other coordinates. You get these sort of pretty patterns. In these sort of, let's say, Chern -1 bands, right, where we see things that seem to appear at a third or a fifth filling of this new type of band that's not a Landau level, we indeed see these fractional T, fractional S states. And in fact, then if you do the calculation, you find that there are states there that can exist. There's a phase diagram. There's a region of stability in terms of the parameters that we tune in the system where they're stable that, in fact, don't break the lattice symmetry, but rather break up the charge. You know, the electrons entangle with each other in such a way that a third of an electron sits on every lattice site, and that's what gives us our fractional T and fractional S. It turns out that, you know, there are, in fact, also states that both break symmetries and have topological order in more complicated bands. I won't talk about it today. So let me just finish with sort of what's useful about this. So, I mean, there's one thing that's kind of useful, which is this sort of new world for us, right? We've, you know, as a community, Quantum Hall have been studying Landau levels for 30 years, right? That's a Hamiltonian we understand pretty well. Now this is some new knobs to turn just to see what do electron-electron interactions do? What's the ground state going to be? But there's actually some really cool ideas that are very different. In particular, it turns out if you combine some of these with dislocations, if you can control the lattice to make a dislocation, you can localize states there that are very similar to the sort of Majorana fermions that people play with superconductivity and spin orbit systems. The difference for us is that, you know, it's easier because you don't have to have a superconductor and a magnetic field, which is indeed annoying in those systems. It's harder because we need to do this in a lattice where we can actually control it on the single site level. So it means going back to lithographic superlattices, and we don't know if we can do that as perfectly. But that's something that sort of we're going towards. But you know, I'll just close with this sort of plot, which I'm very fond of, which is that you know, these samples, so these are often bilayer samples. I sort of elided some of that distinction earlier on. So you have two layers that are coupled strongly together. There might be a superlattice on one of them. You can change the magnetic field. That basically will change the flux per unit cell, but it also changes a number of other things. You can change the in-plane field, which modulates the spin. You can change the density. You can change the electric field across it. The data hypercube of these samples is unbelievably complicated, right? And in this one plot, right, which was taken in, I don't know, an hour or something, you know, you basically have, you know, fractional quantum Hall effects everywhere, including even denominator fractional quantum Hall effects, which are thought to host non-abelian statistics, more exotic, you know, 13/5 states that also should have non-abelian statistics. You have symmetry breaking, you have the lattice symmetries, you have states of multi-components of different spins. You really have like and you have these fractional Chern insulators of various kinds. I mean, this is really a wealth of many-body physics and a lot of experimental tunability. So we have a sort of our work cut out for us just analyzing this one data set, let alone the rest. And anyway, let me just finish with that. Let me acknowledge in particular my first student and my first postdoc who are responsible for most of the work in my current lab. And thank you guys for your attention. Well, I mean, so this is a particularly complicated device. You can go more complicated. I mean, our approach is to just kind of try to simplify things some more and then try to understand that and work our way back up.
So the reason I ask is you can ask people like astronomy and high energy physics. I think even our lab we're now pushing this limit too, where it's a different direction of analyzing the data. Right? You look at it in a different way.
Yeah, so it's a good question. Yeah. Yeah, maybe that's right. I think we know sort of how to take this. If we can take enough of this data in a certain way, it'll be very like batch analyzable. For now, it's still like you need to go back to the lab notebook to figure out what exactly everything means. But yeah, it's a good point.
Do you know much about the phase transitions between different states?
We know something. It's actually going to be the topic of my seminar tomorrow, or at least some part of it will be. I think, what we've studied the most so far has been just phase transitions like this between, fractional quantum Hall states with different quantum numbers, and sometimes those are discrete and sometimes they're continuous, and that's something that there's plenty of stuff we don't understand, some things that we do. I think there's an interesting question to be asked. Sorry, I'm going the wrong way. Question to be asked at least now that we can engineer direct phase transitions, let's say that are between integer states with different Hall conductances or integer states and fractional states with a different Hall conductance, and what happens at those critical points. I do not know. Yeah. So unfortunately, we're working on figuring out how to get this type of experiment to work at a magnetic field smaller than the largest magnetic field we have at UCSB. Then we'll be able to answer that question definitively. Right now, you need resolution to tell whether gaps close or not, and that's hard when you're doing things in Tallahassee. So actually, all the data that I showed after this slide, the ones on this color scheme are compressibility.
Okay.
Yeah, but effectively, it's not so different from sigma XX, yeah.
But do you actually measure the Hall conductivity or Hall resistivity? How good are these plateaus?
Yeah, good question. I mean, so for technical reasons, having to do with my lab just not being very old and it being easier for us to do this than make good contacts, we haven't done much of that. We've done it for mostly purely capacitive. For the even denominator fractional quantum Hall, we've done transport, and also Corey has done transport, and the plateaus are very well quantized, and the energy gaps are very large. I think we're quite sensitive with this technique, so we can detect some states that would be not that well quantized potentially, because we just start to see them becoming incompressible, but not so sure. There are other issues. When we do this, we probably heat the sample up, so if we could do this probably 10 times colder, and there'll be even more stuff. So there's a lot of optimization to do on both ends, and I'm not entirely sure. How gapped is gapped? For our equivalent of the 5 halves, it's very gapped. There you have a multi-Kelvin energy gap, and it's really insulating and well quantized. So. For the fractional Chern insulators, I don't know.
A technical question. So when you build a superstructure,
So yes and no, meaning most of the time not. We're sort of learning how to do that. There's a beautiful technical advance from Corey Dean's group where they can push, in the middle of the transfer, they can push the flakes around with an AFM, and they'll lock into a place. And so we're sort of trying to figure out how to do that. We certainly we can know, for some types of things, we can know the alignment, and we can just try to approximate it, and we do that, and that sort of more or less works. So we've made, let's say, twisted bilayers. We've tried to make them aligned 1 degree, and we've gotten it to be 1.5 degrees. That's worked. That sort of works. It's hit or miss, but it's not that hard to make these samples. So if it doesn't work, you just make another one.
I have one other question, and maybe I'll end this one. So what is your opinion about gallium arsenide? Have they reached the limit where disorder is no longer a problem? And how far are you? Like these devices seem to be at least so clean now that you're running up against much higher order physics than the disorder.
Yeah.
Even to the point of
It really depends. It really depends on the physics that you want. So a good example, right, is, there's an example that's going to paint graphene in a positive light, but if you want something to paint graphene in a negative light, you should ask somebody else. There's a recent beautiful experiment from Modi Heiblum on 5-halves in gallium arsenide measuring quantized thermal conductivity, right? And they get kind of the wrong answer compared to what you would think. And the sort of basic understanding, if there's nothing wrong with the experiment, is that in that particular case, what sets the, what breaks the degeneracy between two particular versions of that non-abelian state might be disorder, and disorder might actually favor some other state. And that's a very subtle question there, right? I mean, there's two states that are very close. In graphene, there are two ways why, let's say, if we did that experiment, it probably wouldn't be a problem. One is that that's not degenerate in the same way, and in fact, we can control that through Landau level mixing and other stuff. And the other is that in gallium arsenide, fundamentally, it's been very difficult to take a plot like this at high quality. Tuning the density is hard and keeping the mobility high. So, we can do experiments at nu equals 1/2 at 45 Tesla if we need to. If the issue is make disorder weaker, compared to everything else, we make everything else bigger and maybe disorder doesn't change, and that's an advantage. The big disadvantage is in gallium arsenide, you make your device 200 times with slight variations in geometry until you get it right. You can do much more complicated experiments. That's very laborious for us because each one is a pain to make, right? So those are the trade-offs right now, but I mean, there's already new physics coming out here that's sort of not possible to do in gallium arsenide, and that's sort of where our focus is now. We'll see. Yeah, I don't know. Why would anybody work at low magnetic fields? I don't know. Let's talk later.